Good morning, all. I welcome you for the lecture series in the course Mechanics of Solids. So let us have a look on the picture which is available in the first slide. So it is of various shafts. Yes, we have seen all these shafts in the integrated system of mechanical engineering, even though, and we need to look into explore the stresses on these shafts. So the twisting force which causes the shafts to transmit power, we call it as torsion. And in this unit, we will explore about torsion in detail. So understanding torsion, the mechanics of twisting shafts, a fundamental exploration of how forces twist and deform structural members. So let us empathize this shaft which is shown here. So it's all about the crankshaft that is being shown here in the diagram. So whenever this crankshaft has a main shaft spindle connected to this, rotates based on the rotations made on the connecting rod connected to the piston. So the torque that is produced or the couple, the force that is acting equal and opposite direction tends the shaft to twist in the clockwise or anti-clockwise direction, so creating a circular motion. So the reciprocating motion in the connecting rod is converted into circular motion to feed the wheel, that is from the engine power is transmitted to the wheels of the automobile. So this is how we have to understand this torsion. So the twisting occurs when a shaft or bar experiences twisting from an applied torque. The twisting action generates internal shear stress throughout the material, critical to understanding structural behavior. So the real world applications are drive shafts transmitting shaft engine power, helicopter rotator blades or rotor blades, industrial machinery components, and structural steel members. So visualizing torsion in a circular shaft, it is all about the fixed boundary and the applied torque, angular displacement, and stress distribution. The key insight from this slide is the stress distribution is linear proportional to the radial distance from the shaft center axis. So what are all the assumptions we normally make in this pure torsion theory? This classical torsion analysis relies on several fundamental assumptions to simplify complex behavior. So one is material properties, that is homogeneous, isotropic, and elastic, obeys Hooke's law throughout. Geometric behavior, cross sections remain plane, no warping occurs during twisting, after twisting also. Shape preservation, circular sections stay circular, radial lines remains radial. Uniform twist, angle of twist linearly along shaft length. Pure torsion, no bending moment or axial forces present. So this is all about the torsion formula we have derived from the shaft. So we have something called as polar moment of inertia that qualifies cross-section resistance to torsional deformation, analogous to the area moment of inertia in bending. So J equal to pi d power 4 by 32 is the formula for solid circular shaft. And hollow circular shaft, J equal to pi the d power d naught power 4 minus dA power 5 divided by 32. So the design principle, larger the J means twist and lower the shear stress for a given torque. Efficient designs maximizes J while minimizing the weight. Coming to the practical implications and design considerations, weight optimization, stress management, and torsional stiffness. So the common application is, again, we have seen all the machineries of turbine blades, automotive sector, and air defense air sectors. So summarizing this video, mastering torsion for engineering success, we have understood what is fundamental principle, stress deformation, and mathematical foundation and design excellence. So coming to the mind map of this particular session, we have defined what is pure torsion and what is the theory assumptions we have made, mathematical functions, and design considerations, real world applications. And here we have a quiz for you. So I hope for a circular shaft subjected to pure torsion, the shear stress varies linearly from zero to the center to the maximum of the surface. That is the right answer. And the torsion equation, we are well versed with option B. So these are all the reference for this particular video. Thank you. Let us meet in the next session. Thank you all.